All right, lesson 3.5. On our calendar, it might say 2 days. I'm just, for the purpose of the video, I'm just going to do one. We got 5 examples. They're all solving. The only difference from section 4 is they all involve applications. But you shouldn't see a whole heck of a lot else. There's one new problem at the end where we're going to write the equation. There we have a couple new things to talk about, but other than that, we're still solving. Let's dive right in. Okay. Always, always, always make sure to read. Make sure you're good on context. That's kind of the first pitfall of modeling and application problems, is many times students don't do a good job reading about the context of the problem, and a lot of times it's hard to answer. Here, it's a exponential growth model, continuous, right? We love base E because that gives us continuous growth, or decay, in this case growth. D is in millions of households, and so what we're after here is, let's say D is 100. What value for T would give us that? Which means we are left with the task of solving that. Okay? Now when you have your equation set up, you should be thinking, wow, that looks a lot like a problem from section 4, right? The deal was in section 4, we would have said, like, I would have given you that formula with no context and just said solve it. You know, you have no idea what T is. It has no practical meaning. You just need to solve it. So you should notice we're going to go through the same steps. I'm going to divide by 30.92. Which would give us that. Because we've done a decent amount of solving, it's never a bad idea if you're feeling pretty confident and you don't kind of need to go through it with me step by step. It's a great idea to pause. You work the problem through and then see if my solution matches. Next step is to take the natural log of both sides. This is eventually going into my calculator, so I don't care to simplify it yet. This is where we do the real damage over here. That cancels, and we don't have an exponential expression anymore, which is good. Because that 0.1171, which is the growth rate, by the way, I don't know if you caught that, it means that at this time the rate of change for digital televisions was like 11.7%. Okay. And we would have one final step here. To get T. What I'm going to have on the left now is what I would put into my calculator. And of course, we are more often than not very comfortable with decimal approximations. We get a little over 10, which means we would hit the 100 million mark in about 2010. And I bet you this data was pretty close to on the money, because if I remember right, the actual switch in terms of signal, with the analog signal being shut off and a full switch to digital TVs, I want to say was 09. Right? And I bet you 100 million households was probably pretty close to feeling like just about everybody was ready for that switch. All right, let's take a look at some logarithmic models. Again, I think this might be the only one. I think the rest of today ends up being exponential. The context is a good one. It's the Richter scale. You might have heard of it. It's how the intensity for earthquakes are measured. I do want to point out here that I sub 0 equals 1. That's a constant, so you're not going to see that show up. All right, so we have data from 2004. The northern Sumatra earthquake. That'd be an interesting one if you wanted to research a little bit. Before your time. Really a significant event. Really, really large, powerful earthquake that set off a bunch of tsunamis near Indonesia. And in terms of the fatality, it was a pretty significant event. I want to say it was on Christmas Eve or Christmas Day of '04. Staggering death totals with it, and something you could look up if you want to explore this a little further. As far as the mathematical side, all we're after is we want to compare, on the Richter scale, how powerful is a 9.0 earthquake compared to a 6.8. Okay, it's a logarithmic-based scale, which means we would set it up like this: 9.0. It's log base 10 of the intensity. Okay, now the book didn't say what measurement or what units intensity gets. I'm not sure myself what it is. It's more of a physics question than a math question. To solve this, I would do 10 to the 9.0 power. There was no base on the log, so I was free to assume that it's 10. And then we get this, that the intensity for this earthquake is 10 to the 9th power. Which would equal that, okay? A large number. Looks to be a billion. Now for the Southeastern Alaska earthquake, it's going to look really similar because it's also on the Richter scale. But we would set up our equation just like that. Exact same step to solve it. Both sides of the equation. Have to be written as exponents with base 10. And those cancel. And now to get the intensity, it's pretty similar here, but we just have to do 10 to the 6.8 power. And you get a very, very different looking number. 6,309,573. Okay, so now if you're just comparing the wave intensity, these we can just compare directly. And if you were to divide them, you would see the 9.0, again in terms of its wave intensity, is about 158 times more powerful than the 6.8. Okay? Pretty enlightening if you know a thing or two about logarithms, that you can see that a 9.0 compared to a 6.8 is a pretty substantially, more powerful earthquake. All right, on example 3, I really like this problem. You're going to see on the steps to solve it, it's pretty darn similar to the first one that we did, but some of you aren't going to feel that way, and you may not even like this one all that much. So here's what's going on. Okay, it's comparing this ratio of two different types of carbon, right? You may have seen it before in, oh gosh, biology class? I don't know. Somewhere in applied science. But it can be used to date things like fossils. So we have a value for r right here that we are going to set up to solve. Because basically what we have is that expression models, you know, how we would date something using carbon-14. What we need is the ratio of carbon in a fossil that we found, which is 1 over 10 to the 13th power. So what you're going to see on this one is the concepts are really similar to number 1, but the numbers aren't quite as nice. We do now have a value for r to put in, though. All that's going on here is my value for r got plugged in, okay? And it's pretty common when I've had students look at this problem in class that they get to this point and they're like, you know, I don't know what to do. And this is when I remind them that the setup at this point is very similar to number 1. Okay, notice if you look back to problem number 1, we divided by 30.92. And we have to do the same thing. We need to divide by that number in front. Okay, it's just a weird number. It's crazy small. It's 1 over 10 to the 12th power. Doesn't change the fact, though, that we have to divide by it. Now we're dividing fractions over there, so obviously that left side is going to need to be cleaned up a little bit. We'll get to it. Meanwhile, the right side actually looks a little bit better. Trying to get t by itself. Here's what you would see on the left side for the next step. I'm going to leave the right side alone. I'm dividing fractions, which I never like to do. So I end up multiplying by the reciprocal, which would be just 10 to the 12th. We get 10 to the 12th divided by 10 to the 13th, which equals 0.1. Okay, now I'm running out of room to go down. If you still have room to go down on your paper, that's fine. I got to switch over to this right column. But at this point, my equation is actually looking a heck of a lot better. I have that. Okay, not too bad. Time to take the natural log of each side. I know that because on the right side I have one term. It is an exponent with base e. That cancels. Oh, the natural log of 0.1, not interested in getting it quite yet. 2 equal signs. Oh, you know, not needed. Now I can be a little bit efficient here. I don't think you'll mind it too much. I'm just going to make sure more clearly that's a negative sign. I need to multiply both sides by 8,223. But notice I got rid of the negative sign. I could do this in one step if I multiplied by negative 8,223. Okay? You have a little bit of a mess over there on the left side, which, you know, doesn't bother us. That just, you know, number for number, letter for letter, that would get typed into our calculator. And it would spit back for us 8,934, that's in years, so that would give us, the best approximation that we could of that fossil based on the levels of carbon-14. All right, I threw it a little bit of an extra one here in part A, just to kind of keep us in check that we're not just solving every single problem without thinking about it, because it's conceivable an application question doesn't ask you to solve. That was more common early on in the chapter. This one is about a flu virus spreading throughout a college campus. Okay, we've got a little graph of what's going on, and like a lot of exponential growth problems, it starts slow and then can really, really pick up over time. How many students are infected after 5 days? What I want you to just see here is that this problem isn't asking you to solve. In fact, this equation is set up really nicely to do this. I have a value for t and 5 that I'm going to put in, and I would see that it's about 54 students. Okay, about 54 students. I'm going to go clean this up a little bit. That was kind of messy. Okay, so you could see the common mistake there that somebody just plugs in 5 for y and then solves. This again goes back to the context of the problem, that you got to be clear on your variables, and you would want to see that t is time, y is students. They gave you a value for t. It's an easier problem than solving. You just have to plug in 5. Now part B, which I'm short on room for, so what I'm going to have to do is kind of do this in 3 columns. You'll have to bear with me a little bit. I didn't think this one through that well on the slide. It does have a few steps to solve to get it, and I did not do a good job of setting it up. Okay. Now it mentioned above that the college would cancel classes if 40% of the student body is infected. That is a number of students, so that goes in for y. So this one we do have to solve. Okay? This one we do have to solve. The first step here is a little bit tricky. All right? And I got to do the best I can to squeeze it in here. I'm going to head over here to maximize some of my space. I would not be super confident you would make this step on our own. You might at this point, in order to see what to do. I'm not sure you would. This whole fraction situation is tricky, and we haven't seen anything like it. We can really kind of address it in one step. Okay? I'm trying to get at t, and it's in a really bad spot right now, but I'm going to multiply both sides by the entire denominator. The entire thing is what I'm going to multiply it by. Okay? Notice the whole fraction situation is gone. Okay? Gone, gone, gone. And this is starting to look a whole lot more like the other problems that we've done. Okay? Watch what happens now when I divide by 2,000. I'm left with 1 plus 4,999 times e to the negative 0.8 t power. When I divide that side by 2,000, I get 2.5. Okay? Just 2.5. The numbers are starting to get a little smaller and more manageable. it's conceivable at this point that you actually see the next step. It is to subtract 1. So we would get 4,999 e to the negative 0.8 times t power equals 1.5. And once we got that first step going by multiplying both sides by the whole denominator, it really turns into a problem that we're much more familiar with pretty quickly. Okay, next step there, divide by 4,999. And now we get to the signature step of an exponential equation, that we are taking the natural log of both sides. As usual on the right side, things are getting a little messy, but, you know, I'm fine with it. It's all headed to the calculator. Again, I apologize. I'm kind of working side to side here. That'll cancel. At the very least, I'll get the columns kind of color coordinated here to keep them clear. Negative 0.8 times t. That left side is looking much better. ln of 1.5 over 4,999. You know, probably at the end of the day, a little decimal. That would be my guess. Whatever that is. And you may find if I were to take the time and go to my calculator to actually get the decimal approximation, I'd probably have less writing to do. You may have seen that if you've practiced these on your own and then compared it to what I do, that I end up having more writing because I keep it written in terms of a natural log and then I go to the calculator at the end. Oh goodness, the right side is just a mess, right? Make sure that this is in parentheses and that it's closed, okay? In parentheses and closed. And you should get something from your calculator. That's a little bit over 10 days. Okay, so 54 students would be infected in the first 5. By the time we get to 10, we'd have 2,000. So, hopefully they'd have some plan in place as to what to do with this by the first 5 days. And you can see that solution is marked on the graph of about 10.1. Alright, this one's got a few steps too, but luckily I thought this one through a little bit and gave us a lot more room to work with. Alright, here's what I'd tell you about this one. We kind of have used PERT for financial problems, but the structure of PERT is actually going to work really well here too. So I'd tell you right off the bat that as far as this problem goes, you would want to use like a PERT model. It's looking at the growth of fruit flies, and it wants us to give the projection for after 5 days, but here's the thing. We don't have an equation, and predicting any population of the fruit flies after we have an equation is going to be pretty easy. But here's all they gave us. They told us after 2 days, there's 100. And after 4 days, there's 300. Okay, I'm treating the days like the x variable, and then the population of fruit flies as the y variable. That's all it gave us. Okay? Now I want to show you how to handle one of this, and I am aware that this is one of those problems that you would really need to see before I could ask you to do it on your own, because it's got a pretty tricky little step to get started. Okay? I'm going to say that equals A. Alright, right away, I'm plugging in 300 into my equation. P would be like the amount of fruit flies that there were to start. How many at 0 days? Okay, that's what we're going to call P. We don't know what P is. To the E, we don't know the rate, but we know we're at 300 when T is 4. Okay, so we basically had 4 things. Actually, well, yeah, 4 total. We knew 2 of them. We don't know r and we don't know p. We've got 2 variables, and if we're dealing with a single equation, that's a big problem. Okay, we can't solve that. Now down here, we're going to get an expression that's going to look virtually identical. Okay? Which leaves us with a system of 2 equations. Which 2 equations, 2 variables, that can be solved. This is the really somewhat crazy step that I think you would probably not realize that you could do. We're going to take both of these equations and divide them. Okay? For our constants at the end, we would get 3. Anything divided by itself is 1, so it's essentially like the p's cancel, and I'm saying that's the original population. I've got 2 terms. They're both base e. I would subtract the exponents. 4r minus 2r is 2r, and we're left with that. Okay? So I know you would need to see this ahead of time, and I'd have to kind of get you going in the right direction by saying, hey, use what essentially is like a PERT model. Like PERT is often used for financial situations, so this is a little bit of a stretch, but it gives us the right structure to set stuff up. Okay, you'd need a little hand with that, and then you would need to see this whole 2 equations and then divide them. But now we are really in business. At this point, I would hope that you could kind of take it and run with it, because you could do the natural log of 3. I'm looking at this right side, and I see it's time to take the natural log. That cancels, because then I get the natural log of 3 is 2 times r, which would mean r is the natural log of 3 over 2. That's our rate. Okay, that's really, really significant to get. That is the growth rate for this population of fruit flies. I am actually going to go to the calculator or to get a decimal approximation for r. It's going to be easier to solve the rest of it. Technically, natural log of 3 divided by 2 is the exact rate. So I've got a little bit of rounding error, but I can totally live with it because I'd rather do that. Because now I'm going right back up here. And you would have your choice of either equation. It absolutely doesn't matter which one you pick. I'm going to this one just because. Okay, just because. But notice now, knowing r is a game changer, because I can go back to either one of those 2 equations that I wrote, and p, that original population, is the only thing missing. Okay? And you might think that we have a long process left to solve and get p. We really don't. We really, really don't. E to the 0.549 times 2 power. Okay, to the 0.549 times 2 power. Okay, that's a constant. Right? I got to make sure that's in parentheses and it's all together. In fact, if I had stayed with the exact value for r, you would see what we just divided by is actually 3. Exactly 3. Now ours isn't going to be exactly that because I have some rounding error. You're going to see if you put an e to the negative, e to the 0.549 times 2 power, it shouldn't be negative. You'll get like 2.99, right? And then you divide it, and we would get like 33.35, okay? We should get 33.33, so we have a tiny bit of rounding error that's just not enough for us to care. Okay, so now we have P and we have R, and the tough stuff is done. Okay, we're in great shape now because we have this. We have a model that represents the situation. Okay, it was a lot of work to get because we didn't have a lot of information to go off of, but we're in good shape at this point, because any question that we want to answer about how this population of fruit flies is increasing over time, it just got a lot easier, okay? Because we now have this equation. The question it's actually asking, how many are there going to be after 5 days? Compared to what we just did, this is a breeze. You just need to plug in 5. When you do that, you'd see you get about 519. I think just a little bit over that. But once we did the work to get that equation, which was not easy to do, right? R was pretty tricky to find. P wasn't so bad once we had R. But once we wrote that equation, not so bad.